Okay, our third and final skill for this lesson is we're actually going to convert polar coordinates to rectangular or rectangular to polar. Here's kind of the idea. If I were to, for example, plot a point right here on the polar plane. This point could be represented, probably the easiest way, doing a positive r and a positive theta as 1, 2, 3, 4 for the r, and theta would be 45 degrees. That would be the polar coordinate for that particular point. Now, here's what we're going to do. It's not as complicated as it seems. Just kind of go with it. What if that same point were in the exact same location on the Cartesian coordinate system? In other words, where things get scary. If I were to take the Cartesian coordinate system and superimpose it on the polar. In other words, line up the origin with the pole, line up the x-axis with the polar axis. Question is, where would this point be in the Cartesian coordinate system? Now, as far as how to figure that out, it's really not as difficult as it may sound. Seems like, boy, this is going to be complicated. You're putting two graphs, one on top of the other. But the idea is we have a means already for figuring out this ordered pair given an r and a theta. It's just something we did a while ago. All right, so let me try to line that up again. This is something we did way back in, could be early February, I believe, talking about the point of intersection of a circle of radius r centered at the origin and an angle in standard position's terminal side. In other words, if we go back to a circle centered at the origin, that's not terrible. Now, I didn't say a unit circle. If we're talking a unit circle, we can talk about unit circles, but I'm just saying a circle of radius r. So that's the ordered pair r comma 0. Right? So whatever that radius is, could be 5, could be 7, whatever the radius of the circle is, some sort of radius. If I draw an angle in standard position, right? This is its initial side, its terminal side rotates counterclockwise or clockwise. Let's just make things simple. That point of intersection, I should be able to figure out, right? By just knowing the radius of the circle and that angle theta formed there, or that angle in standard position. This point here, if you remember, is r cosine theta, comma r sine theta. Right? That's the x-coordinate. That's the y-coordinate. Now, how we justified that, if you recall, is we would draw a simple right triangle. This point right there has an x-coordinate and a y-coordinate. Its x-coordinate is that. Its y-coordinate is that. And of course, the hypotenuse is the radius of that circle. So, if I set up a simple cosine or sine ratio, let's take cosine. If I say, what is the cosine of theta? You would say, well, cosine of theta is adjacent over hypotenuse. In other words, that's x over r. And if I said, okay, what's sine of theta then? What's that ratio? Well, you'd say that's opposite over hypotenuse. That would be y over r. Simply taking these two equations, multiplying both of them, both sides by r, what you obtain is our formulas here. So multiply both sides by r, the r's cancel, and we get r cosine of theta is actually the x-coordinate. And here, r sine of theta is actually the y-coordinate. We mentioned this a long time ago, but it still holds true, and it's actually the way we convert from a polar coordinate given, an r and a theta to a rectangular coordinate, an x and a y. So how do you go from polar to rectangular? Well, you simply say your x coordinate is r times the cosine of theta. Your y coordinate is r times the sine of theta. And that's all there is to it. Well, a little bit of math involved when you have to figure out these exact values, because generally they're going to give you thetas that are recognizable, that are 30, 60, 45s, or have reference of 30, 60, 45s, or your quadrantals. It's not like they're going to give you a 172.5 degree angle for theta. If they give you an angle for theta, they are probably going to give you something that is familiar to us, that we practice pretty hard. So that's the idea. I probably should just formalize this and not be so sloppy. Let's put it over here. We'll say, to convert a polar coordinate that is, your r and your theta. So you're given -3, 135 to rectangular coordinates. Should be saying to a rectangular coordinate, the old familiar x comma y, x coordinate, y coordinate. So you want to go from a -3, 135 to some x, some y. Where would that be located in the Cartesian coordinate system if I superimpose the polar on top of the rectangular? Where would that be? Well, we're simply going to use our x coordinate is found by taking the r, the radius of that circle, times the cosine of whatever theta is. The y coordinate, well, it's just r times the sine of theta. Right. So that's how we're going to do our conversion. This is, it'd be best to just memorize these formulas, though I say memorize, I'm probably going to give these formulas to you on whatever test we might have. So this is our conversion from polar to rectangular. All right, let's see a couple examples. All right, now for these examples, what I usually do is save a lot of space horizontally because I like writing across. The hardest part is definitely not the new formulas. That's not the hardest part. The hardest part is figuring out the exact value of the cosine of that theta and the exact value of the sine of theta. But right after solving trig equations, from last chapter, we should be fairly decent at this. Let's hope so. All right, so example 1. Directions will say convert to rectangular. First one, let's see, we got 10, 60 degrees. All right. So obviously I'm giving you a polar, an r, and a theta. I'm looking for you to give me an x, y. What would this correspond to? So if you were on a circle of radius 10 and you go 60 degrees in the counterclockwise fashion, plot a point, where would that show up on the Cartesian coordinate system? What would be the x and the y coordinate that would correspond to a 10, 60 degrees? All right, well, the idea is x is equal to r cosine of theta. I will get this right eventually. R cosine theta. Your y is equal to r sine theta. Like I said, leave a lot of space horizontally. Right. Because what I'm doing is I'm just going to work horizontally with each of these, not underneath like I traditionally do. It just seems easier in the long run. Okay, so we're filling in r is 10, theta is 60 degrees, and 10 sine 60. Now this one isn't too bad. We don't have to work through reference angles. Cosine of 60, sine of 60. Hopefully these are ingrained in our head by now. Let's see what we know. The cosine of 60, well, I'm going to take 10 times the cosine of 60. Cosine of 60 is simply a half. Sine of 60 is your square root of 3 over 2. Multiply these, you will get 5. You will get 2 goes into 10 5 times, 5 square root of 3. So if I said, okay, 10, 60 in polar is what as far as rectangular? Well, it would be the ordered pair 5, comma, 5 square root of 3. The x-coordinate would be 5. The y-coordinate would be 5 square root of 3. That's the connection. So polar plane is definitely connected to the Cartesian coordinate system. There is a direct relationship there. Right? I'll do a couple more examples on the next video. If I could stop this.